Here's a surprising fact to kick things off. Every year, Europe produces over 200,000 tons of coarse wool.
Wow, that's a lot.
It is. And here's the kicker. Most of this wool, it's considered pretty useless for clothing and, often just ends up as waste. It really makes you wonder, what if this waste, this supposedly useless stuff, could actually be turned into something valuable and maybe even sustainable?
That's exactly the question we're plunging into today. We're taking a deep dive into a really fascinating review.
Okay.
It explores the potential of using this often discarded coarse wool in a completely different way, as a key ingredient in composite materials.
Composite materials.
Right.
And our guide for this exploration is a really insightful academic article.
Yes, it's called Exploring the Potential Applications of Wool Fibers in Composite Materials, a review. And it was published in Polymers just this year, 2024.
Got it. So what's our mission for this deep dive?
Well, it's pretty straightforward, but I think quite crucial. We want to pull out the most important insights from this review, show you how these, seemingly humble wool fibers could actually be a bit of a game changer for sustainability in the world of material science.
A game changer, okay.
And also uncover how they might even enhance the properties of the composite materials themselves. So you can think of this as your shortcut, maybe, to understanding a really promising and innovative field.
Okay, let's unpack this then. Composite materials, what are they exactly, and why is sustainability suddenly such a big deal here?
Right. So at their core, composite materials are basically materials made from at least two different components, different parts combined.
Like concrete.
Concrete is a classic example, yeah. Or even some of those advanced plastics you find in construction or, high-tech gadgets.
Okay.
And what makes them so useful is that they often combine the best properties of their individual parts. So you end up with materials that can be incredibly strong, really stiff, but also surprisingly lightweight.
So where do fibers fit into this picture? They sound pretty key.
They absolutely are. The fibers act as a reinforcement within the main body of the composite. We call that the matrix.
The matrix, right.
Imagine it like steel rebar inside concrete. It's a good analogy.
Okay.
These fibers form a kind of network that takes on a lot of the stress, and that significantly boosts the overall strength of the whole material.
And there are different kinds of fibers or ways they're used.
Yeah, you see continuous long fibers often laid out in sheets called laminates. They give exceptional strength, but usually in one specific direction. Then you also have shorter discontinuous fibers. These offer maybe more flexibility in manufacturing complex shapes,
Right.
But the trade-off there can sometimes be how things like curvature during manufacturing might affect their ultimate strength.
And as we sort of touched on, the usual materials for this reinforcement, they're not exactly eco-friendly, are they?
That's the critical point, really. Currently, the dominant reinforcements are often things like glass fibers or carbon fibers. And while they perform really well, their production has significant environmental costs. We're talking climate change contributions, pollution.
Right.
So that's why the search for sustainable alternatives is, it's urgent.
And natural fibers are part of that solution.
They are, increasingly so. Natural fibers are gaining traction as reinforcements or sometimes just as fillers and composites. The real challenge, though, is finding that sweet spot.
The balance.
Exactly. Balancing environmental responsibility with performance and cost effectiveness. It's tricky. And this is really where wool starts to look particularly interesting.
Okay, wool as a potential solution. But let's circle back to this issue of wool waste. It's not, like you said, the nice soft stuff.
Exactly. When most people hear wool, they probably picture merino, maybe, those fine, luxurious fibers.
Yeah.
But the reality is that a huge proportion of the wool produced, especially in the EU, is actually coarse wool. These fibers are they're not suitable for the clothing industry.
And the quantity is massive, right? Not just a bit left over.
It's substantial. We're talking roughly 1.5 to 3 kilograms of this coarse wool per sheep per year in the EU.
Wow.
Multiply that across the whole EU, and you're looking at over 200,000 tons annually.
That's staggering.
It is. And for the wool producers, particularly the smaller ones, getting rid of this quote-unquote worthless byproduct is a real financial burden.
Which I imagine leads to some less than ideal ways of getting rid of it.
Unfortunately, yes. To avoid the costs of proper disposal, some producers have, resorted to illegal practices. Things like burying the wool with farm manure.
Oh, dear.
Or even worse, it's often burned. And you can imagine burning wool releases harmful pollutants into the air, into the soil.
Right. Bad all around.
Exactly. So finding a valuable use for this waste stream isn't just about economics. It's really an environmental necessity.
Okay, so we have this huge amount of coarse wool waste. What actually makes it a candidate for composites? Let's get into the specifics, the characteristics of these wool fibers.
Let's zoom in a bit. A wool fiber is generally, cylindrical in shape. It has an outer layer, the cuticle, that's made of lipids, carbs, proteins. Then underneath that is the cortex. That's about 90% of the fiber, mostly keratin.
Like our hair and nails.
Exactly the same protein. And in coarser wool types, you also find these air-filled cavities called the medulla.
Okay.
But the crucial thing here is that the fineness, the thickness, and the length of these fibers really determine what you can use them for.
And the review actually breaks wool down into categories based on this, like a grading system.
Precisely. Table 1 in the review outlines the main classifications. At the top end, you've got your fine wool. Fibers between, say, 15 and 25 microns thick, longer than 65 millimeters.
That's the merino.
That's your luxury stuff, merino. They have a specific cell structure, ortho and paracortical cells, giving them that natural crimp, that waviness.
Right.
Next down is carpet wool. A bit thicker, 30 to 50 microns, also pretty long. Comes from crossbred sheep or sheep in semi-arid areas. Different internal structure, so less crimp than fine wool.
Okay, and then we get to the coarse wool, the main focus here. What sets it apart?
Right. Coarse wool fibers are significantly thicker, maybe 50 to 80 microns, and they have a lot of that medulla we mentioned, those air cavities.
Air pockets,
Yeah, making up maybe 40 to 80% of the fiber's volume. These often come from sheep in more arid regions. Compared to finer wools, they have fewer of those orthocortical cells. Which unfortunately means they generally have lower tensile strength. They're not as strong when you pull them. Plus, they're often naturally colored, pigmented.
Got it. And there's even coarser stuff.
There is, yes. Kemp wool, even thicker, over 60 microns and over 80% medulla. It's brittle, no crimp, looks chalky white, and it's quite weak.
So what's that used for?
Mostly blended into things like technical textiles or maybe floor coverings. It has a very low proportion of those important cortical cells.
Okay, that clarifies the different types. Now, focusing back on the coarse wool, what are the key physical properties that make it interesting for composites? It can't just be that there's a lot of it.
Not at all. Several properties are really relevant. Let's start with crimp and that natural wave in the fibers. Fine wool has lots of crimps, affecting its feel and spinability. Coarse wool has far fewer, maybe just 1 or 2 per inch.
And that matters in a composite because...
But that difference in crimp influences how the fibers interlock with each other and with the matrix material. That, in turn, affects the mechanical strength, even the look, the luster of the final composite.
Makes sense. What about moisture? Wool's known for absorbing water, right?
That's right. It's naturally hygroscopic. Because it's a protein, it's full of hydrophilic water-loving groups.
Okay.
Plus, the keratin structure has these amorphous, sort of unstructured regions that readily soak up moisture. Wool can actually absorb a surprising amount, anywhere from 13% to maybe 50% of its weight, depending on the humidity.
Wow, up to half its weight.
Potentially, yeah. And this moisture content definitely impacts its mechanical properties within a composite, something to manage.
And felting. I know wool can felt together. How does that play into composites?
Felting, that unique ability of wool fibers to interlock and mat together, especially with heat, moisture, and movement.
Right, like for hats.
Exactly. It's all down to the microscopic scales on the fiber surface. They act like tiny ratchets catching on each other. That's why it's great for hats, coverings, soundproofing, anywhere you want a dense, tangled structure. Interestingly, it's directional, too.
How so?
It tends to felt more easily in one direction along the fiber than the other. In composites, this felting tendency could potentially help enhance the mechanical interlocking between the wool and the matrix, improving cohesion.
Interesting. And just basic mechanics, how strong or elastic is coarse wool?
Well, wool generally has pretty good elasticity. It can stretch and bounce back.
Okay.
This comes from both the crimp and that ratio of ortho and paracortical cells we mentioned earlier. More paracells often means more elasticity.
Right.
The alpha helix structure within the keratin protein itself also helps it recover its shape. But, and this is important when wool gets wet.
The moisture again.
Yeah. It can lose about 25% of its strength and maybe around 30% of its elasticity when wet. So moisture is definitely a key factor to consider in any application.
Okay. And chemically, how does wool react with other materials, like in a composite?
Chemical reactivity is definitely important. It comes from all the different functional groups along the protein chains, and also the sulfide cross-links, those cysteine bonds holding the keratin together. When you put wool into a composite matrix, you really need to understand how it'll react with other chemicals, like acids or alkalis, especially for long-term stability.
So acids and alkalis, how does it handle them?
It's generally pretty resistant to acids, actually. Mild acids are sometimes used in processing, but strong, hot acids will break down the fibers.
Okay.
Alkalis, on the other hand, wool is more susceptible to alkaline conditions. They can disrupt the structure. That said, sometimes a controlled mild alkaline treatment can actually create more stable bonds called lanthionine bonds, potentially strengthening it.
Oh, interesting.
But again, heat combined with alkali usually negatively impacts the mechanical properties. So yeah, the chemical environment within the composite is a big consideration.
All right, we've got a good handle on coarse wool now, what it is, its properties. Let's move to applications. Starting with cement-based composites, that sounds very relevant for construction.
It really is. Wool naturally has some properties that are great for buildings, thermal insulation, acoustic insulation. It's even somewhat self-extinguishing.
Self-extinguishing.
Yes, it tends to char rather than burst into flame. The review mentions the first study looking at wool in bricks was back in 2010. That really kicked off interest in using it in cement, mortar, concrete.
But you mentioned the alkalinity of cement is a problem for wool.
That's the main hurdle, yes. The high pH environment inside cement is tough on wool fibers long term. It can degrade them.
Right.
But despite that, some promising results have still come out, showing improved performance in concrete when wool is incorporated, surprisingly.
Interesting. So how are researchers getting around this alkalinity issue? What are the strategies?
Several approaches are being looked at. One is using additives in the concrete mix things called high-range water reducers, and also carefully controlling how the fibers are mixed in, how they're dispersed.
Okay.
Another strategy is to actually reduce the alkalinity or the humidity within the cement matrix itself, make it a friendlier environment for the wool.
Make it less harsh.
Exactly. That helps the wool fibers keep their structure and better bridge any tiny cracks that form, helping maintain some tensile strength. People are also looking at pre-treating the wool fibers before adding them.
Like coating them.
Sort of, yeah, or modifying them chemically, or even modifying the cement matrix itself to be less aggressive.
And it's not just concrete, right? The review mentioned mortars, even adobe clay.
Exactly. Studies show adding wool can boost properties in traditional mortars, lime mortars too. And that adobe clay study was fascinating.
Tell me more.
They found adding just 3% sheep wool, along with some wheat straw, significantly improved the compression strength compared to plain adobe. It's a great example, isn't it? Taking a waste product, combining it with a very traditional low-tech material, and making it better.
That really is a fantastic example.
Yeah.
What about more standard mortar mixes? Cement, sand, lime?
Yeah, research comparing those types of mixes with added wool has shown that wool can definitely reduce the overall density, make it lighter, and improve the thermal insulation.
Right.
But the common trade-off is often a decrease in the overall mechanical performance, the strength.
Right.
So it becomes about finding the right balance for what you need that mortar to do, insulation versus strength.
So you might insulate better but lose some strength. What specific impacts on things like compressive strength have they seen in concrete?
Studies do indicate adding wool can reduce compressive strength, yeah. Sometimes by 15%, maybe even up to 30%, and fiber length seems to play a role there. But research has also pinpointed a kind of sweet spot. Using fibers around 55 millimeters long and keeping the concentration low, like 0.35% by weight or less, that can actually yield positive effects. And in mortar panels, specifically, optimizing the amount of wool has been shown to improve both thermal and mechanical performance. Some studies even report better flexural performance bending strength in mortars with wool.
And this isn't just for mixing on-site, but also for things like prefabricated panels.
Yes, exactly. There's promising work using wool to reinforce prefabricated clay sandwich panels, the kind used for exterior walls.
Okay.
Adding wool has been shown to make them more resistant to compression, bending, shearing, and it also reduced shrinkage and improved how they handle moisture.
That sounds quite useful.
Definitely. And similarly, when used in insulation boards, while the mechanical strength might drop, the thermal and acoustic insulation properties can be significantly boosted.
Makes sense, playing to wool's natural strengths.
Yeah.
Did the review compare wool insulation to other common types?
It did, yeah. In Table 2, it lines up wool fiber composites against things like rock wool, polyurethane foam, hemp fiber composites, cellulose insulation.
And how does it stack up?
Well, wool looks good in terms of being renewable and biodegradable, obviously. And it offers good insulation. The main drawbacks mentioned are its sensitivity to moisture, as we discussed, and the potential need for treatments to make it more durable over the long term.
So despite the challenges, the alkalinity, the biodegradation potential, the overall idea of using wool as a sustainable, low-cost alternative in building materials seems pretty strong, especially with the push for greener building and easier recycling.
Absolutely. And researchers are actively working on those challenges, using things like metakaolin, a supplementary cement material to counter the alkalinity, or just getting a better handle on the cement hydration process itself. And pre-treating the wool fibers, like with salt water or even atmospheric plasma treatments, has shown real promise for improving their mechanical properties and how well they stick to the cement matrix.
Okay, let's dig into that a bit more, how the size and shape of the wool fibers affect performance in these building composites. It can't just be any wool fiber works the same, right?
Yeah.
You're absolutely right. The specifics matter a lot. Take fiber diameter, for instance. Finer fibers, say in the 10 to 30 micron range, they tend to be more flexible, and they can create a denser network within the composite.
It's good for
thermal insulation. That dense network traps more air. Plus, that extra flexibility can help reduce cracking under stress. And the larger surface area of finer fibers also helps with acoustic insulation.
Okay, so finer can be better for insulation and flexibility. What about fiber length? Is longer always better for strength?
Not necessarily always. Longer fibers do help distribute loads more evenly through the composite, which generally leads to better mechanical strength and stability. Think of them like longer reinforcing bars, yeah.
Right.
But if the fibers get too long, they can sometimes make the mix harder to work with. Clumping, difficulty mixing evenly.
Practical issues.
Exactly. So there's often a trade-off between the reinforcement effect and the workability of the mix.
And crimp, that natural waviness we talked about. How does that help in a solid material like concrete or mortar?
That crimp is actually quite beneficial. It significantly increases the mechanical interlocking between the fiber and the matrix surrounding it.
Like little hooks.
Sort of, yeah. It improves the bond, the mechanical cohesion. That makes the composite more durable, more resilient. Plus, the crimp affects the porosity, the tiny air spaces, which, again, influences both thermal and acoustic insulation.
And the internal structure, those scales on the outside, the medulla inside.
Also quite important. That outer cuticle layer, with its scales, definitely helps with mechanical interlocking, giving the matrix something to grip onto.
Okay.
The cortex underneath can absorb and hold moisture, which we know affects durability. And the medulla, that air-filled core and coarser fibers, directly adds to the thermal insulation by trapping air and lowering density.
So the air pockets are key for insulation.
They really are. Both from the crimp and the hollow structure of the medulla in coarse wool, they create these insulating pockets that minimize heat transfer. So by carefully choosing and maybe processing wool fibers based on these characteristics, diameter, length, crimp, internal structure, you can really start to tailor the properties of the composite for specific building needs. It's about strategic design for sustainable, high-performance construction.
Okay, let's switch gears now. The review also talks a lot about using wool fiber reinforcement in polymer-based composites. Plastics, essentially. This opens up a whole different set of possibilities beyond cement.
Absolutely. The potential for putting wool fibers into polymers is really exciting. You could create novel bioproducts or make traditional plastics more sustainable. Wool offers itself up as this abundant, renewable, and often cheaper alternative to things like carbon or glass fibers in polymer composites, too.
And the benefits sound similar in some ways. Insulation, maybe good mechanics, plus biodegradability.
Exactly. Thermal and acoustic insulation, potentially high mechanical properties, cost-effectiveness, biodegradability, lightweight, all attractive features for polymers. And because of these advantages, people have successfully put wool fibers into a really wide range of polymer matrices, both thermoplastics, which soften when heated, and thermosets, which cure permanently.
Thermoplastics are pretty common, right?
They are very widely used. They're versatile, relatively cheap to process, and you can easily modify their properties by adding fillers, which makes wool a really interesting candidate.
But just like with cement, there must be challenges mixing wool, which loves water, with polymers, which usually hate it.
You hit the nail on the head. That's a primary limitation. The fundamental chemical difference. Most polymers are hydrophobic water repelling. Wool is hydrophilic water attracting.
So they don't naturally bond well.
Exactly. This incompatibility can lead to poor adhesion right at that interface between the fiber and the polymer matrix. And weak adhesion usually means weaker mechanical properties for the final composite.
Right.
Plus, studies show that while adding some wool might initially boost strength, if you add too much, the strength can actually start to drop off again.
Why is that?
Potentially due to the fibers getting damaged or broken down during the mixing or compounding process, especially at high concentrations. Thermal attrition, basically.
Okay, so challenges exist, but the review does highlight successes, right? Where has it worked well?
Yes, definitely. In polyester matrices, for instance, some research surprisingly found that adding more wool fiber actually increased tensile strength and hardness up to an optimum around 50% wool by weight.
50%. That's a lot.
It is. And these polyester wool composites also showed decent mechanical properties overall and good impact resistance.
What about epoxies? They're common thermosets.
With epoxy resins, adding wool didn't seem to hurt the initial mechanical or shear properties. But interestingly, it did improve thermal characteristics.
How so?
It increased the temperature at which the composite started to decompose, and it reduced thermal conductivity. So basically enhanced thermal stability. Even in other thermosetting polymers, adding just a small amount, maybe 3% wool, proved viable for tweaking mechanical properties like ductility, tensile strength, and how much work it could take before failing.
And what about really common plastics like polypropylene, used in packaging, cars?
That's an interesting case. Because of the compatibility problem, researchers often use something called a compatibilizer. A compatibilizer like malinized polypropylene. It's an additive that helps the wool fibers disperse better within the polypropylene matrix, bridging that hydrophobic-hydrophilic gap.
Does it work?
It helps with dispersion and can improve stiffness, but sometimes it actually impairs the tensile strength, possibly because fibers still break during blending.
So tricky.
But there's been more promising work using a green pretreatment on the wool first, using superheated water hydrolysis.
Superheated water?
Yeah. It seems to break down the wool surface slightly, creating more compatible chemical groups, leading to better interaction with polypropylene and improved mechanical results. Even using finely ground wool powder, made by freeze milling, showed good dispersion and decent properties in polypropylene.
So treatments and compatibilizers seem crucial for polymers. What about the newer bio-based polymers? Are they pairing wool with those?
Yes, absolutely. Exciting work there, too. In bio-based polyesters, using a compatibilizer like PVA allowed researchers to get over 40% wool content, which significantly boosted adhesion and stiffness, though strength at break was reduced, maybe due to short fiber length.
Okay.
And modifying wool fibers with saline silicon-based chemicals before adding them to matrices like malinized linseed oil or polylactic acid, PLA, that really seemed to help.
Ow.
It enhanced the fiber-matrix interaction, increased stiffness and how much it could stretch before breaking, and even made the composite more water-resistant, more hydrophobic.
That sounds promising. And it's not just rigid plastics. You mentioned paper and biomedical use.
Yeah, exactly. Hydrolyzed wool fibers treated with that superheated water again have been mixed with kraft paper pulp
To make
materials that are 100% organic, compostable, biodegradable, but still have decent mechanical and insulating properties. Think packaging or agricultural uses.
Cool. And biomedical.
Yeah, people have made porous scaffolds like frameworks for tissue growth using PLA and treated wool. These showed antibacterial properties and good strength.
Wow.
And even more advanced stuff like combining wool fibers with silver nanoparticles to create composites that are both antimicrobial and antistatic. Lots of potential there for medical devices.
Okay, we've seen again and again that getting the wool fibers to stick properly to the matrix, whether it's cement or polymer, is absolutely critical. The review stresses this fiber matrix adhesion. Why is that interface so vital?
It really is fundamental. Good adhesion is what allows the stress, the load, to be efficiently transferred from the usually weaker matrix material to the stronger reinforcing fibers.
Passing the load.
Exactly. Strong adhesion ensures the whole composite holds together mechanically. It optimizes its ability to withstand forces without falling apart.
So a strong bond lets the fibers actually do their job of strengthening the material.
Precisely. When the bond is strong, loads get transferred effectively across that interface. This reduces the risk of delamination where the layers separate, and it enhances the overall durability. In building materials, where structural integrity is everything, this strong bond means the fibers can take the load from the matrix, significantly boosting strength and stiffness.
And it helps with cracking, too.
Yes. When tiny cracks start to form in the matrix, fibers that are well bonded can bridge those cracks. They hold the material together, increasing its resistance to crack growth, making it tougher overall.
Makes sense.
And thinking back to wool's moisture sensitivity, good adhesion can also act as a barrier, helping to protect the fibers from water getting in and degrading them.
Okay, so adhesion is key. What factors influence how well wool fibers actually stick to a given matrix?
Several things come into play. First, the surface of the wool fiber itself. Its physical texture, those cuticle scales we talked about, can provide some mechanical interlocking like tiny anchors.
Right.
And its chemical composition matters too. Surface treatments, like using alkalis or silanes, can change the fiber's surface energy or add new chemical groups that can form stronger bonds, either chemical or physical, with the matrix.
So modifying the fiber surface. What else?
The matrix formulation itself is crucial. Choosing the right type of polymer or cement and potentially adding those compatibilizers or other additives we mentioned can really promote better interaction.
Okay.
And finally, how the fibers are arranged matters. Their orientation and how evenly they're distributed throughout the matrix impacts adhesion and load transfer. You want uniform stress distribution for the best performance.
So it's a mix of the fiber surface, the matrix chemistry, and the physical arrangement. Now, how do they actually make these composites? What are the manufacturing techniques?
The review covers several common methods. One of the simplest is hand layup.
Hand layup.
Yeah, you literally lay the fibers down by hand in a mold, then pour the liquid resin like epoxy or polyester over them. Then you use a roller or brush to make sure the fibers get fully soaked and to squeeze out any trapped air bubbles.
Sounds straightforward.
It is relatively. You usually coat the mold with an anti-adhesive first so you can get the finished part out easily. A variation is spray up, where chopped fibers and resin are sprayed into the mold at the same time. Faster, but maybe less uniform.
Okay, those sound like basic methods. What about more advanced techniques for better parts?
For more complex shapes, better precision, and nicer surfaces, you have things like resin transfer molding, or RTM. Here you put the dry fibers into a closed mold, sometimes arranged as a pre-shaped structure called a preform. Then you pump a low-viscosity resin into the closed mold under pressure. It flows through the fibers and then cures.
Advantages.
You get dimensionally accurate parts, really good surface finish, and you can make quite thick composite structures this way. There's also vacuum-assisted RTM, or VRTM.
Adding vacuum?
Exactly. You apply a vacuum to the mold, which helps pull the resin through the fibers more effectively, can be faster, and help reduce voids.
Okay. And for really big structures, like boat hulls or wind turbine blades?
For those, resin film infusion, or RFI, is often used. You lay down layers of dry fiber in an open mold, but instead of liquid resin, you put down a solid film of resin.
A solid film?
Yeah. Then you cover the whole thing with a vacuum bag, seal it up, and put it in an autoclave, basically a big pressurized oven.
Heat and pressure.
Right. The heat melts the resin film, the pressure and vacuum force it to flow into and saturate the fibers, and then it cures. Great for large, high-performance parts.
What about methods more suited for high volume, maybe with thermoplastics?
Compression molding is one. You take a preheated charge of material, often a sheet or dough-like compound containing the fibers, and polymer, place it in an open heated mold. Then you close the mold and apply high pressure.
Squashing it into shape.
Pretty much. For thermoplastics, you cool it under pressure before removing. For thermosets, curing happens under heat and pressure, no cooling needed in the mold. And then there's injection molding.
Very common for plastics.
Hugely common. Probably the most widely used for mass production of polymer parts and composites. It's great for high precision, complex shapes, relatively low cost per part.
How does it work with fibers?
It's a cycle. Material pellets, often pre-compounded with short fibers, are fed into a machine. A screw melts and mixes the material, then injects it under high pressure into a closed mold. It cools and solidifies, the mold opens, and the part is ejected. Very fast cycle times.
Okay, quite a range of techniques available. So we've covered the science, the manufacturing. Where are we actually seeing these wool composites being used? Or where is the most realistic potential?
Well, the main driver, as we keep saying, is finding value for that waste wool, the stuff not good for textiles.
Right.
So the construction industry is a huge potential market. Things like insulation boards, wall panels, maybe roofing materials, other building components.
Offering what advantages?
Potentially lightweight, durable, maybe some fire resistance, and definitely tapping into wool's excellent natural thermal insulation.
Beyond buildings, where else?
The automotive and transport sectors are definitely looking at natural fiber composites, including wool potentially for interior parts. Think dashboards, door panels, trim pieces. Weight saving is key there. And the review mentions other possibilities too. Lightweight sports equipment, maybe. Eco-friendly packaging, furniture chairs, tablecops, even those biomedical uses we touched on, like orthopedic implants, and maybe even aerospace for certain interior parts or non-structural components.
So the potential application space seems really broad, but like any new material technology, there must still be hurdles, limitations, challenges before we see wool composites everywhere.
Oh, absolutely. Big challenges remain. One major one is the inherent inconsistency of the raw material, the wool itself. Its properties can vary quite a bit depending on the sheep breed, where it was grown, how it was harvested, how it was processed. This variability makes it harder to guarantee consistent performance in the final composite.
Right, unlike synthetic fibers.
Exactly. Moisture absorption, as we've hammered home, is another big one. It affects stability, poses challenges during manufacturing, storage. We also just need more research to really nail down the best ways to optimize that fiber matrix adhesion for different systems.
Okay.
And let's be honest, in some really demanding applications, the mechanical properties you can get from wool reinforcement alone might just not be good enough yet.
So what's the path forward? How do we tackle these limitations?
The review points to several key areas. Continued work on pre-treatments for the wool physical or chemical methods like alkaline or silane treatments to reduce that water uptake and improve compatibility and bonding.
Refining the fiber surface.
Yes. And developing methods that are efficient, reliable, reproducible. Also, optimizing the matrix formulations specifically for wool fibers. Another interesting idea is hybridization.
Mixing wool with other fibers.
Yeah, combining wool with some synthetic fibers like glass or maybe even carbon in the same composite. The idea is you might get some of wool's benefits like lower cost or sustainability, but the synthetic fibers could help boost mechanical properties and reduce overall water absorption.
A best of both worlds approach.
Potentially, yes. Needs careful design, though.
And looking at the big picture of sustainability, are we sure using wool this way is truly better overall?
That's a critical question, and the review really emphasizes the need for more comprehensive life cycle assessments, LCAs.
LCAs?
Yeah, detailed studies that look at the entire environmental footprint, from growing the wool to manufacturing the composite, using it and disposing of it or recycling it. We need those rigorous LCAs to truly quantify the benefits and any potential negative impacts.
To make sure we're not just shifting the problem.
Precisely. And to help make informed decisions about material selection and product design, we also need more investigation into cost effectiveness and scalability. Can we actually make this stuff affordably on a large industrial scale?
Right.
And finally, a really significant gap, the review points out, is the lack of standardized testing protocols, specifically for wool-based composites. Without standards, it's hard to compare results between different studies or for industry to adopt the materials confidently.
Okay. So wrapping this up, it really sounds like we're sitting on this huge, currently undervalued resource with all this waste wool.
Exactly. This deep dive, based on that 2024 review, makes it pretty clear. These often discarded coarse wool fibers have significant potential. They can be sustainable reinforcements, sustainable fillers, and all sorts of composite material.
Ongoing real benefits.
Yeah, enhancing material properties, contributing to sustainability goals across different sectors, construction, biomedical, potentially others.
And while there are definitely still challenges, hurdles to overcome, the future for these woolly composites seems quite bright.
Indeed. Optimizing them is an ongoing process, no doubt. But the active research into refining the processing, the treatments, exploring new applications, it holds great promise for really unlocking the full value of this abundant natural resource.
So let's leave our listeners with this thought. We're talking about potentially transforming a massive waste stream into a valuable, sustainable resource. Could this approach, this way of looking at wool, be a kind of model for how we rethink other overlooked materials in our push for a more circular economy? What other waste materials out there might hold surprising potential if we just take a real deep dive into their properties? Definitely something to think about.